All right, Lauren and Tom, I think we'll go ahead and get started here.
Perfect. Thank you, Seth.
All right.
Go ahead.
Super. Well, thank you everyone for joining this webinar. I'm Seth Johnson, for those of you who don't know me, with Powerside, and today we're here to talk about our power systems analysis program, which we consider to be a reliable way to root out power quality issues. Obviously, power quality is a very large domain, and we'll get into kind of the specifics of what we do here at Powerside. But thankful and grateful for all of you who are attending today, and look forward to a good presentation. And I think we'll have it open for some questions at the end, which can be typed in via chat, so we can answer those once we conclude the presentation. All right, so quick, we're going to do just a basic overview of the agenda for today. I'm going to do an introduction to Powerside, just so for those of you who don't know our history can get an understanding of who we are as an organization and what we do. We'll get into the main topic of this webinar, which is, of course, the power systems analysis overview. We'll talk about the reporting functions as well as QubeScan. We'll touch on target customers and who's certainly interested in this program that we're offering. And then we've compiled 3 different case studies, all of which use the power systems analysis program to come up with a power quality resolution or solution based on our product portfolio. And so we'll go through that and touch on that. And then, of course, talk briefly about our products and solutions, and then hopefully have some time for questions. So, quick company overview. A lot of people don't necessarily realize this, but the company actually started in 1948 under the name of Power Survey, which is based in Montreal, Quebec. Now, our Quebec operations are still based here in Montreal, and we actually started off as an organization doing power system analysis and power studies. So the irony here is that what we're offering here with this power systems analysis program actually dates back to our roots of what we do as an organization back in 1948. And we primarily offered that analysis and that service to companies like Hydro-Quebec for power systems analysis on utility power distribution, or at customer load sites. And then from there we transitioned into capacitor bank and passive filter manufacturing, which many of you are familiar with. A big part of our business, of course, both low and medium voltage power factor correction and harmonic filtering. And then in around 2015 we got into power electronics, specifically in the active harmonic filter domain. And you'll see here in a case study I present later how we use the active harmonic filter with this power systems analysis program. Then we have another organization originally called Power Standards Labs, which was formed in 2000 based out of Alameda, California. They offer power quality monitoring equipment and power system testing and measurement, so phasor measurement units, power quality analyzers, etc. The 2 businesses merged in 2016, and then we're now doing business as one company since 2019 under the name of Powerside. So we have 2 operations, one in Montreal and one in California. The reason why that's pertinent to today's discussion is because we're using equipment from both facilities for this, for the monitoring and detection side of it, as well as the correction and the solutions side of the business. So first, I'd like to talk about kind of the overview of the program. So I mentioned, earlier that the Alameda business manufactures power quality analyzers, and it's a very high fidelity power quality analyzer, which is a Class A device from a hardware perspective, which ultimately can do various functions, but looks at well over 3,000 different parameters at any given time. It offers trending data And then it also does waveform capture. So when there's an event detected or a power anomaly, such as a voltage sag or a transient or a high inrush event, you can trigger an event with the PQ3, which captures the waveform at 512 samples per cycle. So it's very precise in terms of its capabilities. And one of the things that we've done at Powerside is, because of the capabilities of the P-Cube are so detailed and so great, we've offered this in a portable form. And that is exactly how we use it for our power systems analysis program. So we have our lovely P-Cube, which sits inside of a enclosure here with a power supply and all of the connections. And it's also equipped with a 4G modem. And this is really important for this program because as we send these out into the field, we're actually able to connect up to them remotely from basically anywhere in the world, which is fantastic. One of the age-old problems with power system studies is getting a measurement device installed and making sure that it's installed correctly. We see data oftentimes from customers that will give us power quality data, and we quickly realize that the CT was reversed or it wasn't connected properly, and then they have to rerun the study. And so that's a really big added benefit to this program, is the ability to remotely connect up to the portable device as it's installed at the customer facility. Now that does, obviously require a cell service of some sort. We're primarily offering these in US and Canada, but we do have cellular modem in there with extension antennas, to help get better service if it's required. And primarily what we're using this for is, we're focusing on harmonics, power factor, voltage, current, real power, reactive power, flicker, imbalance, and mainly targeted around what we offer from a correction solution. And we're doing this both at low voltage and medium voltage applications. So we've got clients that we've sent this out at 208 volt power systems, all the way up to 230 kV class, I think was our highest. So low voltage, medium voltage, and technically a high voltage application as well. And we're typically installing this at the main service entrance or close to the point of common coupling. The idea of this program is that it's really designed to look at a full power system, not necessarily an individual panel or an individual load. Now, there are some exceptions to that rule. For instance, if a client has a rectifier that's producing a lot of harmonics upstream, okay, maybe we want to look directly at that load individually. But this program is not designed to do a load study to determine if you can add more load to your system. It's very much focused on power quality, which is why we're using, such a high fidelity Class A power quality analyzer. There's certainly other products out on the market if you're just trying to do a basic load study. So, from a process standpoint, you ask for the analysis, we send the portable out, we'll have it pre-configured, ready to go for the application. We usually like to let it run for 1 to 2 weeks, depending on the application. And then a lot of the value of this program is the reporting that we do. So we'll touch on that here in a couple of slides. But the reporting is quite detailed in terms of what we can offer, and it also gives pass-fail criteria. So where do we like to install this device? So here I've got an image of a P-Cube. This is just a basic single line diagram that we put together. And the idea here is you got your transformer and then your main breaker that's feeding the facility. And ideally, if there's nothing tapped off the transformer, we like to be on that secondary side of that main breaker, or sometimes in the main transformer, depending on the configuration. And this is so that we're able to see the full load and the full system. We can certainly look downstream at some of these loads. But again, a lot of what we're doing for the analysis is to make sure that we're meeting compliance standards for things like power factor, voltage imbalance, harmonics, things like that. And so making sure that we're looking at the entire power system is really the idea behind this program. And to install it, like most meters or analyzers, you need access to a voltage source as well as current source. So here on the right here, I've got an image of essentially what our voltage clamps look like. These are fused alligator clamps that you would put on A, B, and C phase, and so you're looking at the full the full three phases coming in, as well as neutral and ground. Now, if this is a medium voltage or even a high voltage application, we would connect these through PTs, of course. Most applications in medium voltage and high voltage have PTs available, which usually bring voltage down to 120. And then we just simply program that ratio in the recording device, the PKeep3 here, so that we're getting accurate information. And then we offer these Rogowski coil type CTs. These are great because they work for a very wide range of ampacities, specifically at low voltage. And then we can also tap into existing CTs if they are at the facility. And one of the ways we like to do that is to take a 5 amp split core style CT and just put that around one of the leads that's going to the existing CT, so that we can basically, in a very non-intrusive way, get in and get the data that we need to provide a report and hopefully propose a solution. So again, there's many different ways that this could certainly happen, but the idea is to get a full power system view of the facility and the loading, so that we can determine whether or not they're meeting the criteria that they need to meet, which is certainly one of the reasons why they would have come to us for a power systems analysis study. So what do we provide? So we provide a very detailed report. It's well over 20 pages in most cases. Here's some screenshots of an actual report that we did. We like to make sure that we give pass-fail criteria, so it's fairly easy to look at and understand what it is that we're looking at. So from a high level, we're looking at voltage, flicker, total harmonic distortion, individual harmonics, total harmonic distortion for voltage, as well as individual harmonics for voltage, and then of course power factor. One of the reasons why we focus on this, of course, is because from a solutions portfolio standpoint, we primarily play in the power factor correction as well as harmonic mitigation solutions. So most of the time when we're sending out this product to do a power systems analysis, it's because the client believes they're suffering from either a harmonics related issue, or they need to maintain a specific power factor and they're not quite sure what it is. Now, of course, in the report, we're going to provide a lot more detailed information regarding the load and all of that. But generally speaking, we're really targeting towards the harmonic distortion, voltage, as well as current and power factor. And then one of the things that we offer is an IEEE 519 report. So I talked about the power quality analysis. And one of the things we can do is, if a client has specific targets that they want to hit for harmonics compliance based on EN 50160 or other compliance standards that are out there, we can easily do that. But we also have the ability to look at IEEE 519, which is really the most common compliance standard for harmonics in North America. And this is a really important standard because pretty much all utilities in North America have a requirement that their customers have to meet this IEEE 519 compliance standard. However, not all of them do, or know that they aren't meeting these standards. And later on, I'm going to talk about a case study where it was really driven by a utility who found out that they were having a harmonics issue on their power distribution grid, and it really boiled down to a customer not meeting 519 compliance. Now, 519 compliance is a compliance standard at the point of common coupling, so it's where the utility and the customer connections basically meet, and it's looking at both total demand distortion as well as total harmonic distortion for voltage. So I won't go into the details of IEEE 519, but this is a real case scenario that we looked at for a client in the oil and gas space where they were exceeding their IEEE 519 compliance for both total demand distortion as well as voltage harmonic distortion all the way through. You can see here, this is for a very large spectrum of harmonics. So, this is a 6-pulse drive load primarily that we're seeing here. And this is a spectrum you would expect to see, but it was on a very weak power distribution grid. So the effects of the current harmonics on voltage were quite significant. And so, we had to deploy a solution to meet the standards required by the utility power provider. And then one of the unique features about our power systems analysis program is that it is equipped with 4G modem, which, excuse me, allows us to utilize our cloud-based platform called QubeScan. Okay, QubeScan is a fleet management platform that we've developed here at Powerside that allows us to look at large fleets of P cubes that are deployed in various locations, and it's got many great features such as live metering function, so you can actually connect up to this QubeScan and look at what's happening in real time. And it obviously provides all the trending data. So everything that the hardware does itself, the PCube3, it brings that data up into QubeScan, and then QubeScan has some further analytics and reporting capabilities, which is quite beneficial for this program. And one of the things that we like to do when we are connected and we have a client that has installed one of these portables on their power system, we like to show them what's happening in real time, because it's quite powerful for customers to see what their load profile looks like, and the fact that we can show it in real time really shows some of the advantages to this program, and of course the high fidelity data. So all of this data that you see here is real data that we've captured in the field. And with the way that QubeScan is set up, we've got various aspects that we can look at to drill down into things like harmonics and peak demand. You can see down here, I've got a peak demand at this site of 1,000 kW basically. This is the peak 15-minute demand for that month. And so there's a lot of versatility that this brings us when we send these out into the field, which again just allows us to provide data quickly to our customers, provide an analysis quickly, and hopefully, of course, a correction solution. So who is it that's interested in this? Here's kind of a diagram of how we operate here at Powerside. So, obviously, many of you may be familiar with us. We have other regional managers in the territory, responsible for Canada and different parts of the U.S. And then we rely heavily on manufacturers reps as a part of our market strategy. So we have about 20 manufacturers reps who cover North America, and between us all working together with the rep agency as an extension of our sales force, we're targeting folks like utilities, engineering firms, OEMs, distributors, and value-added resellers, contractors, and end clients. And really, there's a use case for all of these players. So utilities being one, certainly that we've been working with from a power system analysis standpoint, and a lot of electric power utilities don't necessarily have internal groups that can do power system analysis like this for customers that are connected up to the their power distribution grid. Certainly some do, but some don't. So there's a lot of value in working with a company like Powerside to be able to deploy a meter and provide some engineering analysis for the utility, which then in turn goes to their customer and allows the utility to get more visibility on what's actually connected up to their power distribution grid. So that's certainly one aspect that we target from a market strategy standpoint. And then of course engineering firms, both for brownfield as well as greenfield or new construction applications, where they want to verify that they're meeting compliance after a facility has been built. And then certainly OEMs. So we've worked with large OEMs in the market, switchgear manufacturers, things like that, who are out in the field and find power quality anomalies and are looking for some more sophisticated data. And then a big one for us is distributors. We work a lot with distributors across North America. We've got some great distributor partners who've worked with contractors and end customers that have done a really good job at pushing this program out so that we're able to offer a mitigation solution as well as a detailed report. And of course, contractors and the end client obviously is very interested in this, especially if they're trying to meet a compliance standard that's driven by the utility. So these are all touch points, but the way that I have it kind of structured here is that a lot of these folks all work together. So it's not like the sale goes through one individual entity all the time. It just kind of depends on the scenario and the situation. But ultimately, the power systems analysis program is really a business development tool for us to be able to accurately provide and design a solution that is needed. And that is one gap that we've identified in the market. And I think that's one of the great things about what we're offering as an organization. So let's get into some case studies so that gives you guys all an understanding of how we've used this in the field. So this is a case study for an agriculture application. It was actually a poultry farm in the Midwest of USA. And this came to us primarily because the local utility, which was a small co-op, was complaining about high voltage harmonics backfeeding onto their power distribution grid. So they maintain a fairly small power distribution grid, being a co-op, and they had some complaints about problems with other customers. And so they did some investigation with the tools that they had available. For instance, some of the monitoring that was already in their voltage regulators and in their substations, and they could see that they had a high THD coming back into the substation. And they weren't exactly sure why it was, but they had a feeling it was due to this newly constructed poultry farm. So the utility was kind of pushing this and pushed the client to hire a contractor to deploy some monitoring equipment. And so that eventually that data got sent over to us because they wanted to look at providing a solution for the harmonics, but the data was insufficient. So for example, they used a meter that was only able to look at total harmonic distortion. It wasn't able to look at individual harmonics, which was something that was needed for this application. Because if we're going to do a filtering application, we need to know what we need to filter and how we're going to do that, because we do have different technologies available to us for that. So they went through that whole process, and then basically we had to redo it again because the data wasn't sufficient. So they worked with us to deploy the power systems analysis program to get the required data for us to properly size and engineer a solution. And this is real world data here that we got from the customer. And you can see here, this is for voltage. We needed to stay below 8% voltage distortion per IEEE 519, and at the low voltage side of the transformer from the utility. And they were hovering in the 13% range, sometimes even higher, depending on the time of day, of course. And you may be wondering, okay, well, what is it that's causing these harmonics? So we were wondering the same thing, which is why they gave us kind of a detailed load list of what they had on site. And this was basically a poultry operation or a poultry farm, and there was hundreds of motors in there that were powering fans in these barns. And there was, I think 6 different barns total at this facility. Now, these motors are what are called ECM motors, so electrically commutated motors, which have what is similar to a 6-pulse drive spectrum, essentially, which basically produces harmonics. And they came to us and they said, well, no, the manufacturer states that these ECM motors meet 519 compliance standards. And first we go back and say, well, 519 is not a equipment standard, it's a point of common coupling standard. And so the issue came into play when they had 200 or more of these on each of these 6 different feeds, which is why you see a voltage distortion so significant. So what we did is we deployed our power systems analysis program, and we pulled this profile from the customer. And you can see here from a pass-fail criteria, they were failing on all the harmonic orders up to the 23rd, and you can see that here in red. And again, this is fairly typical of a 6-pulse spectrum. And generally, the biggest offenders were the 5th and 7th, 5th being the primary. So this was a perfect application for us to provide a power quality mitigation solution. And so what we offered was our Power Act product line. And you can see images here of the actual units that we shipped this client. We shipped a total of 6 of them for this client, 1 per poultry barn. And they're 250 amp active filters. Now, we went with the larger enclosure because we have the ability to add additional modules in the active filter if they expand the load or they need further correction. And so our design from an active filter standpoint is a modular design. Each of these modules is rated at 125 amps. So of course, 2 of them together makes 250. And then we have space for 2 more. If we ever need to in the future, we can add 2 more modules to give them, up to 500 amps of harmonic correction. So the utility, after the client installed the active filter, the utility wanted a report. So they again came to us to do another power system analysis to confirm the results that we had initially simulated for the client. And down here you can see the results. So before filtering, we had 330 amps of 5th harmonic, 110 amps of 7th, 68 amps of 11th, 49 amps of 13th. And we brought it down to this down here. So about 83 amps, 20, 29, 20, and 10 amps. So we were well within the spectrum, which brought the total harmonic distortion for voltage down below 5%, closer to 4%. Now we could further fine tune that and get that down lower if we wanted to add some more capacity to the system. But in this case, we're meeting and exceeding the utility power provider's requirements. And so this data was shared with the customer, which ultimately was shared back with the utility power provider, which turned out to be a great application for us. Now you will see these enclosures are painted white. This is used in an outdoor application, and in many outdoor applications, depending on where they're at, we like to paint enclosures white to just help with radiation from the sun, so that we're not overheating any of the internal components inside the filter itself. So really cool and exciting case study, and I do believe we have this in a printed document as well on our website, where you can see more details related to this specific case. Next, I'd like to talk about a case study in a manufacturing facility where we deployed power systems analysis. So this was a aluminum extrusion facility, and this kind of goes back to some of the earlier days of what we do as an organization, which is alleviate power. Excuse me, I got a bit of a cough. Power factor penalties for customers who are not meeting utility power factor requirements. So this particular customer has a requirement of 95%, which is, certainly on the high side. We see anywhere between 85 to 95%. If you're primary metered or metered on a medium voltage side, sometimes utilities will require, up to 98%. And then, of course, if you are KVA build or build for KVA, then you're paying for anything that is not at unity or at 100% power factor. So this particular client was getting charged around $20,000 a month in power factor penalties, which certainly added up over a year span. There was 5 main services in this facility, and all of these services were equipped with existing power factor correction equipment. And although I don't get out in the field quite as much as I used to, I was fortunate enough to go to this facility and look at it. And one of the things I noticed was, all of the power factor correction equipment had failed. Now, of course, it's a dirty environment, it's manufacturing, but I was a little surprised that they failed so quickly, given the age of some of the equipment. So we agreed to do a power system analysis study. So we set out a PQ portable and put it on each of the 5 services, ran them for about 2 weeks on each service. And we basically used our power systems analysis program and the QubeScan platform to look at some trending data over time. And this was fairly eye-opening to us as we were analyzing the load profile at this customer site. And one of the things you'll see here, I know it might be kind of small on the screen, but you'll see that we get a drop in voltage, comes back up, it drops again, it comes back up, drops again. And the voltage drop obviously coincides with the increase in current. And this is actually an aluminum extrusion process where they're pressing a large billet of aluminum through a die. It gets pressed through, and what you're seeing is that pressing process. And so it's very cyclic. It's predictable, but it's very cyclic within an essentially 2-minute time frame. And so correcting for power factor, in this case, we wanted to look at being able to do some more instantaneous power factor correction so that we weren't just using typical contactor switches to correct for power factor. And one of the reasons why we figured out that the equipment on site had failed is because it wasn't designed properly to dynamically respond to this type of load profile. And so again, this is an example of the QubeScan platform that we're using in real time while this is connecting to the customer site, and we're looking at the load profile and the swings that we're seeing in current, reactive power, harmonics, voltage, etc. So what we did is we developed a solution that would allow us to correct for those dynamic points during the pressing cycle. And so this is a hybrid solution with our PowerBar series product line, where we're doing both contactor and thyristor switching. So you'll see over here on the left, we've got contactor switched stages. This is 800 kVAR actually, a contactor switched. And this is going to take care of the base load of the facility. Even when they're not doing the pressing cycle, there's still a very high base load, which needs reactive power compensation. And then as soon as that pressing operation happens, these thyristor switches over here on the right are going to engage and disengage extremely quickly. This happens in about 3 cycles. It can turn on and off. And one of the reasons why you can't do that with your typical contactor switch is because you're basically limited to a minimum of a 60-second delay between turning off a contactor switch stage and turning one back on again. And that's because you have to let these capacitor cells discharge below 50 volts before you bring it back on. When you're using a thyristor or a zero voltage crossing switch, you could turn them on and off instantaneously, because when they turn off, you don't have residual voltage in the capacitor cell, so you do not have to wait for it to discharge. And so when we look through some of the existing equipment on site at the facility, we saw a lot of contactors that were burnt up, a lot of blown fuses, and we went into the some of the control parameters, and everything was set to respond relatively quickly, but it led to premature failure of the equipment. So again, another really cool example of how we were able to use this program to provide not only a solution to mitigate the power factor penalties the client was receiving, but also, and even more importantly, a correct solution that's going to last them a long time. And again, that's one of the unique things that we offer here at Powerside. So this client, they loved the data so much that we provided, that we actually embedded the P-Cube into the correction solution. So you'll see on the right here, this is the panel power factor controller over here, and then we've got our P-Cube embedded in there. And this is going to be able to look at all of the main incoming on all 5 services for this facility, and it's going to give them, full power quality data, which they currently don't have at all. And so this was really a win-win for the customer. And then we even took it a step further by wiring in the alarm contacts inside the controller directly to the P-Cube. So if there's an event that occurs or an alarm that occurs on the capacitor bank, blown fuse is detected, or there's an over voltage condition or something, it will actually send a signal to the P-Cube, which then gets sent back up to QubeScan, and they'll get an alert directly to their email that there's an event that's taken place, and they need to go take a look at the capacitor bank. And this is certainly good for them, because they did not necessarily have a robust maintenance staff there that knows much about this product. So this is just another way we were able to provide some additional value to this customer. And I did do actually a video on this, which I believe is up on YouTube now, if you want to see more of this case in detail. You can find it at our Powerside link on YouTube, or I think it's also on LinkedIn. And then the last case study I'd like to go over here is a medium voltage case study. So I stated earlier that we do both the power system analysis for both low voltage applications and medium voltage. And this was a 5 kV class application for a government institution. And they had reached out to us because they had a significant voltage sag when some of their medium voltage chiller motors started. Now, these motors were on soft starters, okay? So they were limited to, let's say, 300%, max load at inrush, but they were still experiencing a significant voltage drop. And it was causing other electronic equipment to shut down, particularly some other VFDs and other power electronics in the facility. We did this metering at 5 kV, but their point of common coupling was upstream at 13.8 kV. So we actually provided a report for both the 5 kV and the 13.8 kV side, so that they understood the implications of the motor starting and the voltage sags that we're seeing, at 5 kV, but also upstream, and to where the utility point of common coupling connection point was. So what they ended up seeing here was about a 12% voltage sag at 5 kV. So this is actual images that we got through QubeScan of the event that occurred during the motor starting application for this soft-started medium voltage chiller motor. And you can see we're down to 3.6 kV for voltage down here. So certainly a significant voltage drop. And so, they asked us, well, what can we do for you, or what can you do for us in terms of a correction solution? And so one of the things that we can do with medium voltage motor starting is provide voltage support by adding reactive power to the system. So whether the motor is on a soft start or it's direct across the line, there's a significant amount of reactive power that is being consumed during that motor starting process. So you can see here, this is the reactive power that needed to support the motor starting sequence on the soft start, which was just under 3 megavar or 3000 kbar. And that would obviously, if you were able to correct all of that, that would give you a unity power factor. But when we were looking at this, of course, we're looking at providing capacitors. So, okay, we want to take care of the voltage issue during the motor starting, but also we want to correct for power factor. While we're in there and we're adding bars to the system, let's try to tackle both problems at the same time. So we will go to the solution that we had provided here. So what we ended up doing was designing a 1.5 megavar detuned filter. It's in a 3-stage configuration, so 3 stages of 500 kvar. And this is going to be connected, or was connected, with the motor starting sequence of the soft starters. So soft starters would send a signal to our equipment. We would engage a stage or multiple stages depending on the motor starting sequence. And this would improve voltage substantially. I mentioned earlier they needed just under 3 megavar, 3000 kvar of correction to get to unity. We don't need to get to unity power factor during this motor starting sequence. We just need to make sure we're not seeing more of a 5% voltage drop at 5 kV. And honestly speaking, we could have seen a little bit more at 5 kV and been okay, because at the point of common coupling, we're seeing about 2.5 to 3% voltage drop during these motor starting applications. So this system is designed to operate 2 ways. So it goes into a motor starting sequence where it provides VAR compensation and it brings in the stages needed to do the motor starting. And then it will switch over into a power factor control mode. And that's what we have here is a power factor control right here. And so once the motors are up and running, then we're engaging stages of VARs just to maintain power factor, which also helps improve voltage. And this brought a lot of value to the client because we're preventing unnecessary and erratic undervoltage equipment tripping that was happening throughout the facility. And this wasn't limited to just the 5 kV bus. This was happening in other locations throughout the facility. So we were able to get this, from a 12% voltage sag to 5% with this solution. We could have even gone a bit further if needed, but it certainly wasn't a requirement for this application. And then the other thing, of course, was you'll notice that it is a detuned filter. One of the things we looked at during the power systems analysis was the fact that there were a significant amount of harmonics during the motor starting sequence due to the soft starting application for which these motors were being operated under. And so the detuned filter allowed us to dampen the system so that we're not amplifying harmonic content during the motor starting event. So again, another great case study of how we use power systems analysis program to really come up with and determine a solution that the client didn't really know existed, but solved their problems and even went a step further to provide the VAR compensation under normal operating conditions. So one of the things that customers come to us for is they know us because of our products, both low and medium voltage, and I like to kind of say this is our business process here. A lot of clients come to us, say, hey, we need a capacitor bank, or we need an active filter, or we need a medium voltage product. But a lot of times we need more data to determine what it is that the client actually needs. And in a lot of brownfield applications, you'll get into facilities and you'll see equipment that's failed. And certainly, every piece of electrical equipment has a lifespan. But it's good to get an understanding of, whether or not there's been a misapplication for the existing equipment that's been installed. And so we continue to see that as a big gap in the market, which we're trying to fill with this power systems analysis program. And so a lot of times we need a bit of data. So that could be, data from the utility company providing power factor data for the customer's load. It could be a full single line diagram or an ETAP model or SKM model, detailing out the load profile and what is connected on the system. But that kind of leads us to having to offer, services. And this power system analysis is a fantastic service, which is fairly low cost and easy to deploy, and allows us to get data instantly. And I certainly haven't seen very many companies out there that can do that. And I think it's a very unique capability we have as an organization, and a way that we can bring value to our sales channels and ultimately our end customers. And those case studies certainly prove to you why this works. And then at the end of the day, we're selling solutions. So you looked at those 3 case studies. While some of them looked somewhat standard in terms of product, they were all configured in a specific way for this application. And that's really where we do well as an organization in our niche. There's not a lot of folks out there that know all the details about harmonic mitigation, both at low voltage and medium voltage. And our product portfolio certainly speaks for itself in terms of our capability being both at low voltage, and then all the way up to medium voltage. And here's a quick product overview. So we have our Power Cap product series, which we can do in standard power factor correction cap bank, like a static capacitor. We have our filter. We have our Power Cap Auto, which is a low-cost version of an automatic switching capacitor bank. And then, of course, our active filter products over here on the right, which we've introduced into the market in the 2015, which continues to have a very big growth potential, and the trajectory for this product is going to continue to be quite massive in North America as utilities continue to look for and search for customers who may or may not be meeting the point of coupling compliance standards such as IEEE 519. Then, of course, the medium voltage product, which we can do both in a power MVAR product line or a synchro MVAR, so we can do fast switching or dynamic switching. And we can design these as single tune, multi-tune, high pass or C-type filters. And this, of course, has been a growing market for us as well. We primarily manufacture up to 35 kV class, or I should say 38 kV class, in metal enclosed. If you go above that, typically you're into an open rack configuration. And then, of course, our PowerVar series product line, which you saw me talk about in the manufacturing case study, where we did a modified design for both a hybrid contactor and thyristor switched solution. So, from a product solution standpoint, we've got certainly a lot to offer, and really a lot of that value that you're seeing from power systems analysis comes from the reporting and our internal expertise with our applications engineering group, and certainly the portfolio of projects that we've done from 1948 till today certainly makes us a market leader in this segment. So with that, I will open it up with questions. It looks like we have about 10 minutes left to the meeting, and we'll see if there's any questions.
Very good. Thank you, Seth. As far as the chat's concerned, Seth, just want to say Bernard had a question about CSA standards for the P-Cube, which I think I've responded to in the chat. Otherwise, I don't think there's anything in the chat at this time. But if anybody else has questions that they want to put in the chat, or if Lauren, I'm not sure if you can open mics at this point, but certainly I think now would be the time to ask any further questions. But I thought that was very well summarized. Thank you, Seth.
Yeah, I see a question here from Andy. Where can I find information on Manufacturers Rep Agency in Eastern Pennsylvania? What we'll do, Andy, is I'll connect you with your regional sales manager, Amadeo. He's also on the call, and then he'll work with you on that.
Perfect. And I see Richard Lane just asked a question. Are there plans for G5 up to 100th order harmonic monitoring? Obviously, I mean, we can certainly get into the discussion about harmonics above the 50th and supra harmonics in particular, that the P-Cube can do, picking up, especially picking up frequencies in the range of 2 to 150 kilohertz, which is what the new standards are requiring. So happy to take that offline with the monitoring group, or if we, I'm not sure, Seth, you want to go into super harmonics right now, but it is a topic that we're happy to answer.
Yeah, I would say, yeah, thanks, Tom. And I'll let you take that offline. But we are looking at super harmonics on all of these case studies as well. So, or all these studies that we're sending out the Power Systems Analysis program, because the P-Cube, of course, is capable of looking at high frequency emissions up to 150 kilohertz. So yeah, but right now we're primarily using this in North America, where the main focus has been on IEEE 519 for compliance standards. We have seen some deviations from that, of course, based on certain operations, certain client requirements, or some other companies that may be operating here but are headquartered or have operations in other countries, and we can adjust those parameters. But from a technical standpoint regarding the capabilities of the P-Cube, Tom, I'll let you take that offline.
Okay, absolutely, certainly can. Let's continue on questions though relating to correction products. A couple of really good questions just come in, Seth, on the chat. So Charles Tucker, in manufacturing, is there an advantage to the end user to do harmonic correction at various locations in the plant versus doing correction at the point of common coupling with the utility? And I think that's really a very interesting point you might want to touch on.
Sure. Yeah, thank you for the question, Charles. So there's many aspects to doing harmonic correction. One of them, you'll see a lot of VFD manufacturers are going to be putting line reactors on the front end of the variable speed drives. Those are usually 3% or 5% line reactors, or they go to an LCL filter, sometimes called a sine wave filter. These are all good standard practices, but again, you will see that these specifications and these companies will come out saying that the VFD meets IEEE 519 compliance, and the fact of the matter is there's no such thing as a piece of equipment that meets that standard. The standard is a point of common coupling standard. You can meet that standard, let's say, if you put series connected LCL filters on every single VFD. That is possible that you can meet that standard, but the standard is not a equipment related standard. And so one of the benefits of doing a centralized correction approach is that you have visibility at the closest point to the point of common coupling to do the harmonics correction. And depending on how we configure the filter, you can get significant benefits downstream as well. For instance, we can operate the filter in a open loop, closed loop current control mode, or a voltage only control mode. And those are things that we're looking at in all of these applications where we're sending out this power systems analysis, because it's not just about meeting the compliance standards of the utility. While it's obviously important, what's also best for the network downstream. Now, the other thing too that I like to caution people on series filters is that if they fail, it's a series connected device. So then that piece of equipment is down. If you have a parallel connected device like an active filter, if you need to shut it down, typically you can still operate your facility until you get it back up and running. which certainly can help alleviate any pain points to specific operations.
Absolutely. And I think, we do have more material on, the best place to place filters. So I think that'd be a great topic that we can perhaps dive into a little bit more another time. Seth, there's another question from Rick, which is pretty interesting. So are there ANSI or IEEE specifications for acceptable voltage variation for utilities to follow? We install solar, which increases voltage as the system pushes current out to the site, and we sometimes bump into issues with inverters faulting due to high grid voltage. I think that is an interesting topic for both sides of the business, but maybe you could share some experience on your side.
Yeah, sure. Thanks for the question, Rick. It's going to depend on actually the size of the location. So IEEE has a standard called 1547 for inverter-based resources, which touches on this topic. It also touches on harmonics as well. Typically, people have used IEEE 519, but that's more from a load-based perspective or from a consumption perspective. But if you're actually using an inverter to bring power back to the grid, we're kind of widely adopting the standard of IEEE 1547. Increasing voltage is always a concern when you're increasing fault current, essentially by adding solar along with utility power connection. So there are ways to mitigate that. I would say we do that in the medium voltage space, not so much in low voltage. So we'll do that with switched reactors or something similar to like a static VAR compensation to help bring down voltage. We've done this also in solar and wind farms where you've got very long underground cable runs for medium voltage. There's a lot of capacitance in those cables that also increases voltage. But yeah, we have run into that. We've seen that. We do have some solutions depending on the application. But there are standards out there, but I think it really depends on the voltage. If this is a residential application, not so much. If it's a solar or wind farm, that's a different story. We'd probably be looking at IEEE 1547 in that case.
Yeah, I think the only thing I would add to that is, for those that are not converted already, the whole essence of PSA and power quality analysis is to be able to pick up, these signals, pick up the voltage swells, sags that you see on the system, identify them, identify the source, and then have the data in hand to be able to resolve the problem. I think with many sites with basic metering, you obviously see when a resource trips offline, but you don't necessarily know, what the cause is, what the voltage behavior is, and what the high frequency transients or slow transients are. So, I mean, for us as a power quality company, we obviously push hard to get you visibility to what's going on in the grid and then be able to tackle it with solutions. So that's great. Thank you, Seth. Let me have a quick look. I think Michael question, more of a comment than a question, but in response to the solar question, we're seeing more and more cases of customer power factor dropping dramatically when solar arrays are added. Any comment on that first, and then there's another question by Eric after that.
Yeah, you'll see that with smaller solar arrays. One of the things about inverters is that they're actually capable of providing reactive power compensation. However, you're not going to use a solar inverter to do reactive power compensation when ultimately you want it to provide real power out. So we have seen that as well. I would say that more in smaller commercial or light industrial applications, there may be some things they can do from the inverter standpoint, but we've done some projects where we will switch the way that the product or the power factor correction equipment responds based on where the source of power is coming from. And this can go for also a cogeneration site, or or if you're totally go into an island mode, where we need to make some adjustments for how we do the compensation. And that's very easy to do with active harmonic filters, because they also provide reactive power compensation, phase balancing, and harmonic mitigation.
Great point. Seth, I know we're at the top of the hour. If you've got time for a couple more,
Sure.
some real quick questions. Is there a guaranteed grid impedance provided by the utility on the PCC? Is there a difference between commercial and industrial areas? Is a question from Eric. If you want to respond to that, there's one more in the Q&A, I think.
Super. Yeah. So, Eric, great question. The fact of the matter is that there is no such thing as a guaranteed grid impedance by the utility, at least not nowadays, especially with all the inverter-based resources and cogeneration, and we're moving away from centralized power generation, which is impacting really the modern power distribution system. So in most cases, you're looking at worst case scenarios. So we'll work with utilities to give us, they'll run kind of typical scenarios as well as worst case scenarios, and then we'll adjust according to that. Of course, it's always great to get that information from the utility, but again, the modern distribution feeder has evolved from where it was 40 years ago to now, and the impedance, I would say, is one of the things that is on a continuum that's changing depending on what's happening on the system.
Great. Last one, and I think we should probably wrap up, and we can we're certainly open to follow-up questions in the future. But final question from Joseph on active filtering, Seth. What's the max amperage available with our active filtering solutions?
Yeah, so you can parallel as many as you want together, but in a single enclosure, we can do 750 amps in one single enclosure. So that's kind of what we have from an active filter perspective. But we've easily paralleled up to 5,000 amps on a single system. We've also done active filtering through a dedicated transformer up to 25 kV bus, 15 kV bus for medium voltage compensation as well. Perfect.
All right, Seth, really appreciate the presentation. Very informative for me, and I'm sure the audience really appreciate it. I think with any other questions or any other things that come to mind, we're always available at powerside.com, or sales@powerside.com is an email. So thank you, and thank you, Seth, very much for a great presentation.
Yeah, we appreciate it, and feel free to reach out to us, sales@powerside.com, or a lot of myself or Tom, and work with our regional managers and of course our manufacturers reps, and we're looking forward to do more of this. We've got some other content coming out from videos as well as other case studies. So great to be able to present this to you all, and thanks for joining. Take care.